High-voltage transmission lines traverse some of the most unforgiving environments on the planet, stretching for hundreds of miles to link power plants to distant cities. In almost all physical systems, energy degrades over distance. If you force water through a tremendously long garden hose, the friction against the inside of the hose causes the water pressure to drop significantly by the time it reaches the nozzle. Electrical grids operate on this exact same logic. As alternating current flows through miles of aluminum and steel cable, electrical resistance generates heat. That heat represents lost energy, meaning the voltage naturally sags the further it travels from the generator. Except, under very specific conditions, the exact opposite happens. At the end of a long transmission line, the voltage actually measures higher than the voltage pumped in at the source. This anomaly violates our intuitive understanding of how infrastructure behaves. Instead of draining the power, the sheer distance traveled acts as a mysterious amplifier. For this phenomenon, known as the Ferranti Effect, to take hold, a transmission line needs three conditions. It must be long, it must be running at high voltage, and it must be experiencing an extremely light consumer load, or be completely open-circuited at the receiving end. This simplified schematic illustrates a perfect scenario. A grid operator is pushing a heavy 345 kilovolt signal down a straight 200-mile transmission vector. By the time that signal reaches the open terminal at the end of the line, it spikes to 385 kilovolts. Grid hardware is precisely calibrated. An unexpected 40 kilovolt surge aggressively degrades wire insulation. It triggers explosive arcing flashovers between components and can completely blow out substation transformers. This invisible buildup of pressure threatens the stability of the regional grid. To stop it, engineers had to completely rethink how electricity interacts with physical space. A transmission line is not a passive, empty pipe. Every wire possesses three built-in electrical properties: resistance, inductance, and capacitance. Capacitance is the ability to store an electrical charge. We see this heavily in underground power cables. Because their internal wires are tightly packed together inside heavy insulation, they naturally generate their own reactive power as current flows through them. Overhead transmission lines have a much lower capacitance per mile than varied cables. The wires are spaced far apart in the open air, but overhead lines compensate for that low density with immense length. When you string a live, high-voltage conductor high above the ground, the air gap between the wire and the earth acts as a dielectric barrier, the exact insulating material found inside standard electrical components. By extending that wire across a state or a continent, the accumulation of distance turns the entire physical structure into a massive, geographically distributed capacitor. The danger peaks deep in the night. Around 3 a.m., factories are quiet. Homes are dark. Demand drops to near zero. The line is fully energized, but the load is incredibly light. Even without customer demand pulling power, a baseline flow of electricity called a charging current must continuously enter the line. This charging current exists for one reason: to satisfy the massive distributed capacitance of the hundreds of miles of wire. Because this charging current is purely capacitive, it leads the voltage by 90 degrees. When this leading current flows through the line's natural magnetic inductance, the phase shift causes the resulting voltage drop to actually stack on top of the system voltage, physically pushing the wave's amplitude upward. At any single point, that interaction creates only a microscopic rise in voltage. But as the charging current travels across the first mile, the 50th mile, and the 100th mile, those localized increases compound. The sine wave swells larger with every passing tower. A 40 kilovolt overvoltage at the end of the line is not the result of an operator making a mistake. It is a mathematical inevitability dictated by the geometry of the wire and the physics of alternating current. This piece of heavy hardware is a 345 kilovolt three-phase shunt reactor. Shunt reactors act as heavy-duty anti-capacitors. By engaging massive magnetic coils, they absorb the excess reactive power and directly counteract the line's charging current. Without these massive inductive anchors permanently stationed at receiving terminals, long-distance power lines would eventually generate enough internal pressure to physically destroy themselves. Grid operators wage a daily battle against the line's physical nature. In the dead of night, when the Ferranti effect is strongest, the grid requires immediate intervention. Operators manually switch these shunt reactors online, actively dragging the dangerous 385 kilovolt spike back down to a safe, stable 345. As dawn breaks and the population wakes up, the grid changes state. Heavy industrial machinery fires up, and millions of appliances draw current. This heavy consumer load naturally pulls the overall voltage down. Recognizing the shift, operators disconnect the reactors, resetting the network to handle the day's heavy usage. Every minute of the day, the power grid functions as a dynamic, breathing machine. Its fundamental physics shift based on the collective behavior of the population, forcing engineers into a continuous cycle of intervention just to maintain a stable flow of electricity.